Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 61, a 10-foot beam weighing 1,200 pounds is to be moved to the left onto the platform as shown. Horizontal force P is applied to the dolly, which is mounted on frictionless wheels. The coefficients of friction between all surfaces are mu sub s zero point 0.3 and mu sub k 0.25, and initially x is 2 feet. Knowing that the top surface of the dolly is slightly higher than the platform, determine the force P required to start moving the beam. Hint, the beam is supported at A and D because the dolly is slightly higher than that of the uh, platform. So we have to apply the normal reactions at A and D only, as well as the friction. Maximum frictional resistance should be mu sub s times normal, but we'll just call it FA. Then at D also, the weight 1,200, 5 feet from A, half of 10, then at D, ND, and friction, which is FD. So if we isolate the free body diagram of the beam AB, then FA equals FD. So we must decide for the values of FA and FD. Then this is 3 feet, 5 minus 2 feet. Then summation moment about D equals 0, Na times 8 is equal to 1,200 times 3, so Na is equal to 450 pounds. Likewise, summation moment about A equals 0, N sub D times 8 equals 1,200 times 5, or ND times 8 minus 1,200 times 5 equals 0, so N sub D is equal to 750 pounds. Then the maximum frictional resistance at A is zero point 0.3 of 450, and that is equal to 135 pounds, while the maximum frictional resistance at D is equal to zero point 0.3 of 750, and it is equal to uh, 2 to 5 pounds. Since if we draw the free body diagram of the beam, FA should be equal to FD, and since FA is smaller, so therefore it controls. So FA max is equal to 135 pounds, which is less than FD maximum, which is equal to 2 to 5 pounds. So that means FA should be 135 pounds, or 135 pounds, which is FA max. And that should also be equal to FD for equilibrium on the beam, equilibrium of the beam AB. So next we transmit the friction force FD to the dolly, and FD is 135 pounds. So FD minus summation forces horizontal minus P equals 0. So that means P is equal to 135 pounds. So that's it for this problem. Level 62 problem. Determine the minimum force P needed to push the two 75-kilogram cylinders up the incline. The force acts parallel to the plane, and the coefficient of static friction of the contacting surfaces are mu sub A zero point 0.3, mu sub B 0.25, and mu sub C 0.4. Each cylinder has a radius of 150 mm. And this is the given figure. So first, for the solution, let's have the calculation of the weight. weight is 75 times 9.81. So the weight is equal to 75.75 newtons. Then for the free body diagram of each cylinder, for the lower part, let's have the force P applied, then normal reaction, N sub C, then the normal reaction between cylinders A and the upper cylinder, friction, which is going down at C, then normal reaction, N sub A, friction, which is upward, so that the moment of FC and FA will be opposing about the center to prevent the rotation of the cylinder also. Then we have NA transmitted to the upper cylinder, friction, which is now going down, then normal reaction, NB, friction, which is going down, FB, and that's it. So for the lower cylinder, summation forces tangential equals 0. So P minus NA minus 735.75 sine of 30 degrees minus F sub C equals 0. Then summation forces normal equals 0, N sub C plus FA minus 735.75 cosine of 30 degrees equals 0. Then summation of moment about the center of the lower cylinder, then we have F sub C times radius minus FA times radius equals 0. So that means F sub A equals F sub C. Then for the upper cylinder, summation forces tangential equals 0. So you have NA minus FB minus 735.75 sine of 30 degrees equals 0. Then summation forces normal equals 0. NB minus FA minus 735.75 cosine of 30 degrees equals 0. So summation moment about the center, then we have FB times R minus FA times R equals 0. So that means FA is equal to FB. In other words, FA equals FB equals F sub C. Then the maximum frictional resistance at B, because it has the lowest coefficient of static friction, let's assume that it slips, B slips. So FB is 0.25 of NB equals FA. So substitute into this equation here so that we can solve for NB. So NB minus 0.25 of NB minus 735.75 cosine 30 degrees equals 0. From there, we can solve for NB. And NB is equal to 849.571 newtons. Then FA, therefore, which is 0.25 of NB, can now be computed assuming B slips. So FA is equal to 212.393 newtons. Then let's solve for NA so that we can compute FA max into this equation here, because FA equals FB. So NA minus FB, which is equal to FA, 212.393 minus 735.75 sine 30 equals 0. So NA can now be computed, and it is equal to 580.268 newtons. Then the maximum frictional resistance at A is equal to zero point 0.3 times NA, and FA max is equal to 174.08 newtons. But the frictional resistance at A for the cylinders to be in equilibrium is 212.393, and this exceeds FA max. So that means B does not slip. So our next assumption would be A slips because it has the next lower coefficient of static friction. So FA equals 0.3 of NA, which is equal to FB. So Na minus zero point 0.3 of Na into this equation here, so that we can solve for Na. So Na is equal to 525.536 newtons. Then Fa is zero point 0.3 of Na, 525.536, which is equal to Fb, and it is equal to F sub c. So Fa is equal to Fb equals Fc equals 157.661 newtons, which is now less than the answer before. So let's solve for Nb into this equation here. Nb minus Fa here, Nb minus Fa minus 75.75 cosine 30 degrees equals 0. So Nb is equal to 794.839 newtons. Then, having found Nb, we can now compute Fb max, which is equal to 0.25 of 794.839 newtons. So Fb max is 198.71 newtons, and Fb is only 157.661 newtons. So that means point B does not slip, and the value of Fb is 157.661 newtons also. Next, let's solve for n sub c into this equation here. N sub c plus Fa, which is 157.661 minus 75.75 cosine 30 degrees equals 0. So n sub c is equal to 479.517 newtons. Then, having found NC, we also compute FC max to check if uh, the frictional resistance under C is enough to make the cylinders in equilibrium. So 0.4, because coefficient of static friction at C is 0.4 of N sub C. Fc max is equal to 191.8 newtons, and that is greater than F sub C that is needed for the two cylinders to remain in equilibrium. Therefore, C also, point C also does not slip. So for our final answer, so B and C do not slip, only A slips. So P in the first equation, P minus NA, 525.536 minus 735.75 sine 30 minus FC equals 0. So P can now be computed, and it is equal to 1051 newtons. Level 63, determine the range of weights W of the uniform slender bar for which a system will be in equilibrium. Neglect friction at all bearings. So here is the given figure, and let's have the solution. So for the free body diagram, let's have the weight which acts at the center of this bar. So its distance. So let's have the reactions at O also, horizontal and vertical reactions. The distance of the weight from O is L over 2 cosine 30 degrees. And let's have the tension T. And this angle here is also 30 degrees shown. Then we sum up moment about O equals 0. Only the component of T perpendicular to the bar has moment about O, and that is T sine of 60 degrees. Then the moment arm is 2/3 L. So T sine of 60 degrees times 2/3 L minus W times L over 2 cosine 30 degrees equals 0. Cancel out L and solve for T in terms of W. T is equal to 0.75 of W. Then let's do the free body diagram of this box or block, then which is inclined 30 degrees. Then let's have the tension, which is 0.75 of W. Then the normal reaction, the weight, which is 100 pounds. And let's have the superimpose the normal and the tangential axis. And the weight makes an angle of 30 degrees with the normal. And that's the normal reaction. Friction would be up or down because we have to determine the range of values of the weights W. So that's 30 degrees. Then friction 0.4 of N, which is up or down, where 0.4 is the coefficient of static friction. So summation forces normal equals 0. So N minus 100 cosine of 30 degrees equals 0. So that means the normal reaction is 50 square root of 3 pounds. Then summation forces tangential for the range. So 100 sine of 30 degrees plus minus zero point 0.4 of normal minus 0.75 W or T equals 0. So that means 0.75 W is equal to 50 plus minus zero point 0.4 of N, and N is 50 square root of 3. So for the lower limit, we use minus, and for the maximum value, we use plus. So solving for W as a range, so we have 20.48 pounds less than equal to W, and W is less than 112.9 pounds. So that's it for this problem. Level 64, the uniform bar and the homogeneous cylinder each have a mass of 24 kilograms. The static coefficient of friction is mu sub s at A, B, and C, the 3 points of contact. Assuming equilibrium, calculate the normal and friction forces at A, B, and C. And part B, what is the smallest value of mu sub s necessary for equilibrium? So here is the given figure, and let's have in our solution the free body diagram of the bar. Then let's apply the weight, which is 24, so times 9.81, 235.44. Normal reaction at A, then friction rightward, then normal reaction at B, then friction which is up to the right as shown, then the free body diagram of the cylinder. Let's transmit the reactions, but before that the weight also, which is 24 times 9.31, so to 345.44 newtons, then NB, then friction, which is now down to the left, normal reaction at C, then friction, which is to the left, so that the moment of FB about the center will be opposite to that of FC about the center. So next, let's have the line from this point A to the center, and let's call the angle here theta. This is also theta, and the radius, remember, this is 0.333, so that tangent of theta is equal to 0.333 over 1, so theta is arctan of 0.333, and that is equal to 18.418 degrees, times 2 of that is 36.836 degrees. So this is 2 theta. This distance is 0.75 to the center. And remember, from A to B, that's 1 meter as shown in the figure. Because this is 1 meter AC, AB is also 1 meter. We have identical triangles. Then summation moment about A equals 0 from this free body diagram, NB times 1 equals 235.44 times 0.75 cosine of 2 theta. And 2 theta is 2 times 18.418 degrees. So we can solve NB. NB is equal to 141.327 newtons. Then, having found NB, we now compute for FB, set up equations. So remember, this is 2 theta. This is 2 theta. That's 2 theta also. And here we have 2 theta. And this is also 2 theta. So summation of moment about, or summation forces y equals 0 from this free body diagram, NA plus NB 141.327 cosine of 2 theta, so cosine of 36.836, then plus vertical component of FB sine of 2 theta, then minus 235.44 equals 0. So let's have the free body diagram here. 235.44 whole system, 235.44. Then we have Na, then friction, which is to the right, then N sub C, friction, which is to the left. So that means, considering the whole system, Fa equals F sub C, summation versus horizontal. Then, since this is 0.75, so summation moment about A equals 0, N sub C times 1, minus 235.44 times 1, minus 235.44 times 0.75 cosine of 2 theta equals 0. So from there, we can solve N sub C. N sub C is 376.767 newtons. Then Na into this equation, summation forces vertical whole system, Na plus N sub C 376.767 equals 235.44 times 2, or minus 2 times 235.44 equals 0. So from there, Na can now be computed, 94.113 newtons. Then 94.113 plus NB 141.327 cosine of summation forces vertical ladder, or substitute into this equation here. Then minus 235 plus FB sine of 36.836 degrees into this equation to solve for FB. Minus 235.44 equals 0. So FB can now be computed. It is equal to 47.063 newtons. Since FA equals FC, and if we sum up moment about the center here, we can say also that FC equals FB. So that means FA plus FB cosine of, into this equation, summation versus horizontal, FA plus FB, which is 47.063 cosine of 36.836, minus NB sine of 2 theta. This is NB, then sine of 2 theta, 36.836 equals 0. So FA is also equal to 47.062 newtons, which is equal to FC here, and FC is equal to FB because they have practically the same values. So therefore, FA equals FB equals F sub C equals 47.06 newtons to four significant figures. Then NA is 94.11, NB is equal to 141.3, and N sub C is 376.8 newtons. Then the minimum coefficient of friction is equal to, since the frictional resistance is the same, 47.062, then the minimum coefficient of friction is that when the normal is also lowest. So mu sub minimum A is 47.062. Since normal at A is the lowest, so we divide it by 94.113. For the system to be in equilibrium, the minimum coefficient of friction which occurs at A is equal to 0.5001. So that's it for this problem. Level 65, two 8 kilogram blocks A and B resting on shelves are connected by a rod of negligible mass. Knowing that the magnitude of horizontal force P applied at C is slowly increased from 0, determine the value of P for which motion occurs and what that motion is when the coefficient of static friction between all surfaces is mu sub s is 0.4, then part B mu sub s equals 0.5. So here is the given figure. So for the solution, let's have this horizontal distance first. Tangent of 25 degrees is delta AB over 200, and the weight, by the way, is 8 kilograms times 9.81. So we have 78.48 newtons applied as shown. 78.48 newtons. Then normal reaction at A, friction which is to the left, mu sub S times NA. Then normal reaction at B, NB, friction to the left, mu sub S times NB. Then tangent of 25 degrees is horizontal distance between A and B over 200. So that means delta AB is 93.26 mm. So this is indicated 93.26 mm. Then for equilibrium equation, summation forces horizontal equals 0. So P equals mu sub S NA, which is 0.4 of NA, minus 0.4 of NB equals 0. So that's the first equation. Call that equation 1. Then summation forces normal or vertical equals 0. NA plus NB equals 2 times 78.48. Call that equation 2. Then we sum up moment about B equals 0. So P times 100 plus NA times 93.26 plus mu sub S 0.4 of NA times 200, then minus or equals 78.48 times 93.26. So simplifying, combining NA, so 100P plus 173.26 NA equals 7319.045. Call that equation 3. So solving these three equations 1, 2, and 3 simultaneously, because there are only three unknowns, P, NA, and NB. So we get P is 62.78 newtons, NA equals 6.006 newtons, and NB 151.0 newtons. So that means the system slides and P is 62.78 newtons. For the second part, so we establish the same equation, but this time coefficient of static friction is 0.5. So in this equation 1, we just replace zero point 0.4 by 0.5. So P minus 0.5 NA minus 0.5 NB equals 0. Call that equation 4. Then in the second equation, it's the same. NA plus NB equals 2 times 78.48. So that's equation 2 also, same as this. Then In the third equation, uh, we just replace this by zero point 0.5 of Na. So P times 100 plus Na times 93.26 plus zero point 0.5 Na times 200 equals 78.48 times 93.26. So simplifying, 100p plus 193.26 Na then equals 7319.045 equation 5. So solving equations 4, 2, and 5 simultaneously, we get P equals 78.48 newtons, Na equals negative 2.737 newtons, and B is 159.7 newtons. Because Na is negative, it means that this block does not touch the horizontal floor. So therefore, there's no reaction at A. So we just set Na equals 0. Then we sum up moment about B. Take note that there's no Na and there's no friction under block A. So summation moment B equals 0. P times 100 minus 78.48 times 93.26 equals 0. So P is 73.90 newtons. So for the second part, the system rotates about B and P is 73.19 newtons.